Hello everybody and welcome back to Science Live. We're coming to you again from the Creation Education Lab at the Creation Museum in beautiful, kind of sunny Petersburg, Kentucky this morning. It's a great day. I'm joined again by our staff astrophysicist, Professor Danny Faulkner. He might look a little different than he did last week. What's going on with your hair?
Well, it grows fast, and with COVID-19, all the barbershops are closed, so it's got to end soon. I got to get a haircut.
Man, I just take a trimmer and go over my hair. Somebody was posting out on Facebook the other day, hair cutting tips. I said, number 3 trimmer and ear blenders. That's all it takes. It's a great way to take care of those things. But yeah, we're all facing all kinds of different challenges in this time. Barbershops is one we never thought we'd miss, or styling salons, or whatever you prefer. But yeah, so we're here again today, and we're going to be talking some more physics and how things move. Yesterday we talked about the physics of flight, and we'll actually be answering some of the questions that you guys had in more detail for our Friday broadcast this week, and Professor Faulkner is going to help me out with that. And today our topic is force. Okay? And this isn't a Star Wars reference or any of those types of things, but we're talking about the forces of motion around us and as objects are moving and colliding. So when you think of the word physics, how do motion and physics get related to one another, those terms?
Well, physics is the science of the physical world, and things, motion, forces, accelerations, those are all part of the physical world. Mm-hmm. It's all around us everywhere. You hit a ball with a bat, you drive a car, you've got the motor turning the wheels, and that pushes against the earth pushes back. Physics is everywhere around us.
Yeah, I mean, the friction of our feet against the floor allow us to be able to walk. If we didn't have friction, that's an important concept in all this. So we're going to be talking about the idea of force today. So we've got basic mathematical formulas that describe the world around us. So a mathematical formula is something that gives us a description of the way God created things. So what are the two formulas we've got on the sheet here today?
Okay, the first one we call Newton's second law, because Sir Isaac Newton devised 3 laws about 350 years ago of motion. Mm-hmm. This is the second one, and it says, well, F is force, M is mass, and A is acceleration. Maybe I should define those terms a little better.
Sure.
Force is basically a push or a pull. If I push on something like this calculator, just give it a little push, or I pull on it, the result's the same either way. So it's a push or a pull. That's kind of a vague way of putting it, but I think most people can get into that.
Yeah.
Mass is a little tricky. That's a measurement of how much stuff you have, how much matter you have.
The stuff quotient.
Yeah, the stuff quotient. So we have some different mass objects here. We have a light, what are these made of? Plastic?
Those are plastic marble.
Plastic marbles.
Yeah. Mm-hmm.
And we have a regular glass marble here. And then we have a collection of several. We have some large glass marbles. Now, they're made of the same material, so this one's going to be more massive. More massive.
It has more stuff.
Yep, and the most massive we have here will be these ball bearings, probably. Well, the glass.
Yeah, the glass
will more. Yeah, it's bigger, even though it has less density.
Okay.
So mass is how much matter that you have. You can decrease the mass by changing what the substance is made out of or making it smaller. Mm-hmm. All right. And then the third thing is acceleration, and the way we define that, we say, is the time rate of change of velocity. That's very complicated. If something's moving, I'll just take a ball and I'll roll it across the table a little bit like that. The ball is rolling. It has a velocity. It's going to slow down because of friction, but it has a velocity. But if I want to make it go faster, that means I have to make it accelerate. So now its velocity is going to change more quickly, like that, and that requires that I push on it. Mm-hmm. That is, I apply a force. And so Isaac Newton was able to figure this out. The relationship between those 3 quantities is force is equal to the product of the mass and acceleration.
That's a pretty simple formula to describe such complex realities.
Oh, yeah. And I might want to mention the units as well. We generally measure mass in kilograms or grams, and we can do that by putting things on a pan balance. The acceleration is usually measured in meters per second squared. Mm-hmm. Could be centimeters per second squared, but the standard is still meters per second squared. So when you multiply those together, you get kilogram meter per second squared, which is kind of wordy.
Funky.
So we redefined that to be a Newton.
Well, that's handy.
Yeah.
So we've run into lots of terms like that in units.
Yeah.
We talked about amps and volts and those things when we talked about electrochemistry named after scientists. So
Sure.
here's another example where a unit of measurement's named after that scientist.
And it's appropriate we do Sir Isaac Newton that way because he wrote the book on this, literally.
Absolutely.
Yeah.
Okay, so let's talk about using this idea of force. We'll get back to the second equation in a few minutes. So we've set up a couple of marble tracks here, and these are going to help us demonstrate force equals mass times acceleration. So let's get a quick measurement of the mass of each of the marbles. So weigh that plastic marble for me.
All right.
And its mass is 1.11?
1.11 grams.
All right. I'm going to mark that down over here.
Now for the ball bearing, I'll do it next.
Okay.
All right. And it's 8.35 grams.
All right.
I'm glad you're writing this down because the last time we did this, we kind of forgot the numbers. as we
Yeah, I
went.
kept making up numbers every time you'd say one.
Now, the marbles, you want to do the big one or the small one?
The small one.
Small one, okay. Oops, hold on. I didn't put it where I'm
Sit
supposed
still.
to. There. And then we get 5.24 grams.
Okay, so we've got a clear difference in the masses of these.
And on the table, you can see they, from left to right, they get from larger to less mass.
Yeah, so the plastic marble is the least massive, or we could say the lightest. I know that's a term of weight, but
Right.
for what we're doing, weight and mass are pretty much interchangeable.
Yeah.
Okay?
Though they're not the same thing.
Yes.
We've got to be careful about
Yes,
that.
absolutely.
All right.
Okay, so we're going to demonstrate the force that's created by these by moving them through here. So since the plastic marbles are lightest, they will fall more slowly, right?
No.
Oh, I really knew that wasn't right.
But it's a common misconception.
It is.
People somehow think that lighter things fall more slowly and heavier things fall more quickly. In fact, Aristotle said that, and that was science, subtle science for
Yes.
2,000 years. A guy named Galileo 400 years ago challenged that.
Yes, he did.
And the thing is, I think what Aristotle did is he said, well, drop a big rock and drop a feather, and you'll notice the big rock falls really quickly and the feather doesn't fall very quickly. And he said, oh, what's the difference between them? Well, they're different weights, so therefore heavier things fall more quickly.
But he forgot about
Well, he didn't know about
Air resistance.
air resistance, a type of friction. And you know what Galileo did over 4 centuries ago is he did kind of an experiment we're doing. He set up a little Lego track, if you will. They have Legos back then, I don't think. But he set up a track. What he wanted to do is he wanted to slow that motion down. You know, the big legend is he dropped different sized balls off of the Leaning Tower of Pisa.
Yes.
Turns out that probably never
That's
happened.
probably one of those legends
Yeah.
of science.
But what he did is he set up different types of tracks and made them really low. And what that does is it slows the acceleration of gravity down because it kind of stretches it out. And when he did this, he found out the balls rolled down at about the same rate. And we'll test that right now if you'd like.
Yeah.
So you want to start with the most massive one we have, or do you want to
Sure.
start with...
Well, let's start with the lightest, the plastic.
Plastic you want to put on this track first, or
All
the
right,
other track?
so if we start with the lower track, and these marbles are going to roll off onto the floor here.
We'll get them later. You ready, folks?
We'll get them later.
Here it goes. Well, you see its speed that it had.
The amount of time that took, and here I've got a higher one. So this one's set up about 57 centimeters. That one's about 40. And it really doesn't go noticeably faster.
But it was a little faster.
A little bit.
A little bit. Now we can try maybe one of the ball bearings.
Yep.
All right.
I'm going to catch these, though.
All right. All right. And this one you're going to notice goes about as fast as the other one did. Maybe a slightly faster, but not much faster.
Not much.
Try it on the bigger track.
On the bigger track.
And it does go more, I look at it, it goes more quickly on that one. Again, the higher track is going to give you more velocity because the acceleration of gravity is acting longer because this one's a lower height, that's a higher height. The higher you make it, the faster it's moving. You kids, you can try this at home. Take a ball of some sort, hold it over your head and drop it and see how fast it's moving when it hits the floor. And then take the same ball and drop it just above the floor, and it's not going to be moving very fast at all.
Yeah.
The important thing is the acceleration is the same. We call that little g. It has the value of 9.8 meters per second squared, or 32 feet per second squared.
Yeah, and that's a value for on the Earth.
Yes.
Because that's related to the gravitational pull of the Earth.
You
If
go to
we
the
were on
moon, 1/6
it'd
of
be
that.
about 1/6
Yeah.
of that. Yeah.
And it depends on how massive the planet is and how big it is. That's really
Yeah.
beyond what we want to do
And
today.
technically, we could go to sea level versus the mountain, and we'd find variations. But 9.8 meters per second squared is the relative value that we use.
Works pretty well within 1% all over the
Yeah.
Earth's surface. Not a problem.
Okay, so if we think about the acceleration due to gravity, if that's the same everywhere on the Earth, then theoretically, I could drop the rock and the feather. If I try to remove air resistance, if I did it inside of a large vacuum tube where there's no air resistance, what would happen with the rock and the feather inside of a vacuum?
They would fall at the same rate. At the lab where I used to teach, we had a glass tube about that long, and it had a coin and it had a feather in it.
Yeah.
And I could turn it up like this, and the coin would drop right down, the feather would go like this. But then I hook it to a vacuum pump.
Yep.
You pump it out, and then you flip it up, they would fall at the same rate.
Yeah.
And one of the Apollo missions, I think it was 15 or 16, they had what they called the Falcon, was the name of the LEM, the Lunar Excursion Module. They gave them names.
Yeah.
And one of the astronauts took with him a large falcon feather on the moon, and he had a hammer that they used on some of the things they had put up. And I remember watching this live on TV. I was in high school at the time.
Wow.
Yeah, that was a long time ago.
Man.
And he held these up over his head, and he dropped them at the same time. Now, the gravity was 1/6, so it fell some more slowly. It made it easier to watch than on Earth.
Yep.
And they hit the ground at the same time. He picked them up and did it several times.
Yeah, because there's no atmosphere, there's no air resistance
Yeah.
on the moon to interfere with
So it's hard to see that on the Earth generally because you don't have access to a large vacuum chamber and this sort of
Yeah.
stuff. But it does work.
So theoretically, if I were to take one of these marbles and let's say I was shooting a rifle, I had the barrel at a flat trajectory with the Earth, and I drop the marble at the same time as I shoot the bullet from the same height, how would they hit the ground?
If it's on flat level ground, they'll hit the ground at the same time.
Even though the bullet's gone a much further distance,
That's right.
it's still falling the same height.
And
the
I remember-
acceleration of gravity is going to make that occur over the same amount of time.
I remember doing this in high school physics almost 50 years ago. We were, first thing you do in physics, any physics class, is you do forces and accelerations and so forth. I remember this debate we were having because a couple of students just didn't quite get it. I remember one guy went up to the front of the board. We had chalkboards back then, and he tried taking an eraser and slinging it along the tray.
Yeah.
It's projected like this, and somebody else dropped their other eraser, and they both hit the floor at the same time. One of them was 13, 15 feet out, but the other one dropped straight down, but they hit the same time. So it's difficult for many people to see that. They think if something's moving along horizontally, somehow it overcomes gravity.
Sure.
No, as soon as it leaves the barrel of the gun or the support that's underneath it, it's going to start falling at 9.8 meters per second squared.
And you could do this today with like a cell phone camera that has the slow-mo function on it. You could roll something off a table and drop it and get at the right angle to see both of them land, and you'd be able to see them land.
Cell phones
Pretty much
make
the same
lab
time.
experiments a lot better than they used to be.
Absolutely. All right, so let's talk about our second formula
right.
here. The second equation we've got is the equation for work.
Yep.
Now we can make lots of forces, but the goal is to get these forces to do something for us generally.
For
So
instance,
how does the work equation
for instance,
work?
if I have a car with an engine running and I take off in the car, it starts really gunning the engine, putting it in drive or letting out the clutch and going whatever. It has a force acting on the wheels, which then accelerates the car. And as long as you have that force acting, you're going to make the car go faster and faster and faster.
Absolutely.
So we do the physics to derive this, but we have work indicated by the letter W is equal to the product of force and distance. Now we've already encountered the force being in newtons, and the distance we've encountered, it's going to be measured in meters.
Meters.
So if you multiply those two together, you get a Newton meter, and we can leave it that way, but many times we define that to be the joule, Joule.
Again, named after another scientist.
Yep, I think his name was James Prescott Joule.
Yep.
And he was a guy in the 19th century, brilliant man, did a lot of work in energy and thermodynamics and basic physics like this. So we honor him by calling it the joule. In the English or engineering system, it's just simply the foot-pound, and we leave it that way.
Yeah.
So you can do it either way. So when you act on a force on something, then it gives us a certain amount of work. Now, with these balls, when we let them go down the track, gravity acted on them. It produced a velocity, And when it entered the end of the track here, it had a certain amount of force acting, of a certain amount of energy. We call it kinetic energy.
Because
energy.
kinetic means movement.
Energy of motion. Things that move have mass. They have kinetic energy. Now, in this equation, the work is equal to force times distance. Now, we said the acceleration is the same for everything, but the masses are different.
Yeah.
So if we have the plastic marble, the glass marble, the ball bearing, since they have different masses but the same acceleration, they will have different forces, and hence they have different forces, they're going to have a different amount of work.
Okay, so we could measure that with a distance then, because the force times the distance is going to tell us how much work.
Now we're going to do that in kind of a crude way.
Crude, yes.
Yeah, it's going to be real crude.
This is a relative experiment.
But it's clever.
But it's clever to see how things can move.
Then we have just a little box here, sitting here. It's not very heavy. And if you put a little force on it, you'll make it move. So the idea is that we're going to roll the ball down. It's going to hit that box. And when it does, we have a collision or an impact, if you want to be really fancy about it. It will be doing work on that object. And the more energy or more work that the ball has coming down, the farther it will travel. So my prediction is when we do the plastic ball and let's say the ball bearing and then the marble, it's going to move that thing a different amount each time.
Okay, because each has a different mass, it should produce a different amount of work.
Right.
Which will translate, in our experiment here, the demonstration, into a different distance.
And the distance actually is going to be related to the amount of friction, which gets technical, but it scales nicely because the friction presumably is the same in every case.
If we use the same box in every example, we've got it on the same piece of paper, the friction should be the same. So we're keeping those variables constant, and that's a good piece of experimental design. Okay?
So we're going to take one marble.
All right.
Are you ready down there? And I'm going to release it. And it didn't move it very much, did it? Can you measure that?
So I'm going to measure the length here. The distance that it moved is roughly 2 millimeters.
2 millimeters.
So
you want to write that down?
2 centimeters. All right.
Write that down. 0.2 centimeters.
So we're going to record that over here. We're going to do 3 trials.
Because you should do more than just one.
Yes. Make sure we're
In fact,
getting
10 or 20 would
results.
10 or 20 would be better, and we could do a standard deviation, all that kind of stuff. But
let's just go with
don't
3
worry about
today.
that, kids. All right, we're going to do a second time. We're ready. All right, let's get a measurement of that.
So get a measurement here. Again, I'm going to call it 0.2.
Okay, 0.2. All right, you write that down. I'll do a third experiment on it. All right, and once you measure that, when you get done writing that down.
You're making me do all the work.
Yeah, that's what I'm here for.
That one's a little less. I don't think it moved quite as much, but it's a little bit of an angle. I'm going to call it 0.1, but still pretty close.
Okay, very good. Now we're going to move up to the glass marble, right?
So this is more massive.
About almost 3.5 times, almost 4 times more massive. So I'm going to guess it's going to move maybe 8 centimeters, maybe 7 centimeters.
Okay.
I mean, 0.8. Yeah, not quite a centimeter. Let's see if I'm right. All right. Oh, it went farther than that, obviously.
Okay, so again, we're going to make the measure from the front of the paper. And I've got to get that at the 0 line. I'm going to go 3.7.
3.7. Okay, it's a bit more than that. There's something else going on here, obviously. Not sure what it is right now. But let's see if we get the same result when we do it 2 or 3 more times.
Oops, centimeters. That's a C, not an O.
All right, here we go.
Okay.
Bounce about the same, it looked like.
3.6.
3.6. All right.
That back.
Write that down. I'll run it one more time. Make you do all the work again. I'll do the fun stuff. Okay, we got to bounce off of it again.
I'm kind of taking the middle since it's a little bit of an angle.
It kind of twisted each time, didn't it?
Yeah. I'm going to go 3.5 on that one.
3.5. So the average would be 3.6. So it's like, 18 times more than the other one was.
Yeah.
Wow.
So 3.6 would be a good average value. Here, I'd probably call that one 0.2. All right.
So it's about 18 times more, isn't it?
Yep.
Quite a surprise. All right, but it is gretter, which we expected it. Now, quantitatively, we may have not been right about that. Okay, the ball bearing is 8.35. If we're going to compare it to the glass marble, it's going to go maybe not quite twice, I would expect. So maybe around 7 centimeters.
Yeah.
Let's see. All right. All right.
Okay.
Oh,
Measure
wow.
there. About 7.9.
7.9. Okay, not almost about double what we had before.
Yeah.
Okay, I'll start a second experiment on this. Oh, wait.
Uh-oh, we didn't get it set up.
Didn't get it set up right.
All right, we'll pick that one up later.
The ball was the ball. We had a ball on the track. I forgot it was there.
There we
You
go.
did too. Okay. Okay.
All right. This one
That made a more complicated experiment, didn't it?
I did. Introducing variables. And go 7.8.
7.8, very close to what we had before. I'll take the ball off the track this time. Twist every time,
That
doesn't
one
it?
twisted a little. So to kind of get this more consistent,
Take
7.9.
7.9.
We'd want to figure out a way to get that to move straight.
Right, 7.9. So we're getting an average of around 7.9 for that one.
Okay.
And notice it's a little more than twice of what the other one was. I suspect there's something more complicated than what we're doing with a simple analysis here, because the friction is probably playing a key role there.
Yeah.
But at least qualitatively, it shows you what's going on. The more mass you have, the more work you have, the more energy you have, the more work you do on the box.
Yeah.
Simple as that.
So we've been able to clearly demonstrate that the force increases the amount of work. There's no
Yeah.
doubt about that.
Yeah.
Coming up with all of the fine-tuning of the formula and all of those things would take some work to figure out all the pieces there. But you can see these are simple ways we can demonstrate that God has created the world in an absolutely uniform way. That uniformity of nature is a signature of His character, that He's put His laws into play in nature, and that we can then study these things and learn about Him by learning about His creation. All right, we thank you for joining us again, and we hope you will come back one more time for us. And tomorrow we'll be discussing some very interesting things with animal fingerprints. Hope to have an exciting thing happening for you. And until then, get out and enjoy God's creation.